This meeting is being recorded.
We lost your share. Did we lose Dana? Oh no. Dana, where did you go? Let's see. There he is. Are you there, Dana?
Back. For some reason, it disconnected. I don't know why.
Okay.
Well, so a point I tried to make last week, and I am going to try and revisit it right at this moment, is that the world is really overwhelming, and the world of science is overwhelming. The information just never ends, and I think, and another issue is when we start to get older, we start to forget things that were so valuable to us. It's just a point of interest to me that I think the bottom line is nurturing a state of mind and not a state of deep information. And the state of mind would be something along the way of a sense of astonishment at the way the world is, or a sense of wonder, or any other word that heightens our appreciation of the world. I think that's the value of learning about the world, because information-wise, there's just no end to it. So if I could have, if I'd gotten back to this program this morning, I would have shifted things. Oh, I do need to see if I can get my share screen to work. Is that showing?
Yes.
Yeah. Well, there's the atmosphere is in the mid latitudes where we are. It's only 6 miles thick. It's a little thicker at the equator, and it's the only thing that stands between us and annihilation. That's a point of interest to me. We would definitely not exist if it weren't for this thin atmosphere that guards us from the cold emptiness of space and the cosmic rays that come from the sun and from space. So it's sort of only by the grace of strange natural processes that we're here. So the weather is largely about the atmosphere, and we'll talk more about the atmosphere for sure. But I read that, so 6 miles thick in the mid latitudes, if you were to, it would be on a globe, it would be like a thin coat of varnish. It would be invisible. You would not be able to find it. And yet, in many ways, it's everything to us. So,
Hey, Dana, do you want to put the slideshow on?
oh, sorry, I don't know. Oh, yes, I think
See
that's
up there on your,
yes.
yeah, there you go.
So the weather's driven by the sun, and the sun is impressive, you have to admit. It's and the whole arrangement for life on the planet is actually quite bizarre. And at the moment, I'm thinking of the fact that the sun is 93 million miles away. It's fusing 600 million tons of hydrogen a second. That's not comprehensible. It's fusing it into helium. There's a very small amount that is turned into energy of that 600 million tons. A very small amount of energy, a very small amount of mass is turned into energy, and you're looking at it. We call it the sun. And that's what drives climate and weather on Earth at 93 million miles away. And there is a little dot there with, I drew a red arrow. You can see the relative size of the Earth relative to the sun. The sun is 1 million times larger than the Earth. So I'm going to not talk about this slide for a minute. We're going to get to some pictures of what I want to say, but it struck me that really the Reader's Digest version of the weather, what causes weather, not so much climate, but our weather, would be summarized by the tilt of the Earth and and the Coriolis effect, the rotation of the Earth. So we'll talk about that. But those are the two things that drive the weather everywhere, actually. So this is the beginning of our little list of Goldilocks effects, which I mentioned that term last week. And it's a fascinating phenomenon. So the Earth is in the habitable zone. Of all the planets, the Earth is the only planet in the habitable zone. And what that means, if nothing else, it's the only place that water exists in three states: as a liquid, a gas, and frozen as ice. And it easily transforms between those three all the time. And if there was no liquid water, there would be no life. So the habitable zone is pretty meaningful. So that's a Goldilocks effect. We're in just the right distance from the sun at 93 million miles. I got interested enough in this that a few days ago, I started a list. I'm up to 32 Goldilocks effects. I think they would not end. I think they could go on forever. But here's a short list that I think are interesting. Mountains. Mountains are eroded to self-destruct, eroded at nearly the same rate they are built. If it weren't for plate tectonics, the Earth would be flat. But because of the particular arrangement of the heat in the Earth and the movement of the plates, the rate of erosion is about the same as the rate of mountain building, and we have the planet as we experience it. I would call that a Goldilocks effect. Salt has been running to the sea for 4 billion years, but the seas don't get any saltier. How's that possible? How is that possible? Actually, I'm not 100% sure how that's possible. Some of it is sequestered in sediments and disappears from the surface of the Earth. But it's just an interesting phenomenon. The nutrients necessary for life they're dissolved in water and they run to the sea for 4 billion years. But we've never run out of the nutrients necessary for life. Why is that? It's because of plate tectonics. It's because ocean crust is subducted down into the magma and reappears as magma at volcanoes and mid-oceanic ridges. You know, it's just strange. The sun's fusing 600 million tons of hydrogen per second, just the right amount to keep the Earth warm, and it doesn't run out. How is it possible that it does not run out? I may have mentioned this last week, and you may be well aware of this, but the Earth, when the Earth formed in orbit around the sun, it would have formed at 90 degrees to the sun, not tilted. And it is tilted at 23.5 degrees to the sun. And it seems to have happened because a smaller planet, they call it a planetesimal, smashed into the Earth early in the accretion of the solar system, when there was a lot of debris in orbit around the sun, and it knocked the Earth over to 23 degrees. If that had not happened, there would be no seasons, because that's what it would get hotter and hotter, hotter and hotter at the poles, and colder and cold, hotter and hotter at the equator, colder and colder at the poles. But somehow it happened, and this comes up not infrequently. These catastrophes that seem so ruinous create an improved living situation for life on Earth. You could argue that the asteroid strike 65 million years ago, that appears to have eradicated the dinosaurs, made it possible for mammals to radiate out into the global environment. The massive explosion of the Yellowstone caldera 2 million years ago, which left ash up to 2 feet thick, even in Nebraska, 1,000 miles away. In the end, it was fertilizer and made all the soils more fertile. Earth is a strange place. So the tilt is just right for distributing the heat of the sun throughout the planet. And that's what makes the weather, and the climate is distributing the heat from the star. Otherwise, it would all accumulate on the equator, and there would be no distribution. And that's the story of weather, is distributing the heat. How is the Earth? So James Lovelock, many of you know his name, he first spoke of the Earth as Gaia, as an Earth goddess, as something alive. He took a lot of flack for that. It does act like it's alive. So then he started calling it an Earth system, and now we have Earth system science, and it really is not 100% different from Gaia or ecology, that everything is connected to everything else. So these, let's see, I think I have a little red circle here. These are the layers of that 6 miles of atmosphere or 10 miles at the equator. Yeah, they show some larger numbers, but it's so thin that they guess they don't even count it. So I actually tried to look this up. Why is the lower layer of the atmosphere is the troposphere down there at the bottom. At the top of the troposphere, it's minus 70 degrees Fahrenheit. At the top of the thermosphere, it's plus 2,700 degrees Fahrenheit. I looked that up yesterday. I could not figure out why that's the case, because there is no air up in the thermosphere to speak of. The atmosphere is so thin there. It's said that the molecules are heated up because they're in such unprotected close contact with the sun that they must be moving awfully fast, because that's the measure of heat, is movement. Anyhow, it's a strange phenomenon. And, if we had to live in the upper troposphere, we'd be dead. But fortunately, we live in the lower troposphere. So things work out. The composition of the atmosphere. I mean, as I go through these, I keep getting hit by the Goldilocks effects. So what do I mean by that? The atmosphere is nitrogen, mostly nitrogen and oxygen. Both of those are pumped into the atmosphere by life. There would be no nitrogen and no oxygen if it weren't for life on the planet. So that's an example of at least Earth system science, if not a living planet that keeps conditions right for life through its own functioning. And you see that it's got a leg to stand on. There's something mysterious here. Oxygen is the second most reactive element in the periodic table after fluorine. And what does that mean? Remember, we talked about electron shells. I'm all about electron shells. They're so interesting. Well, oxygen wants to combine with other elements. It doesn't like being oxygen. It wants to make carbon dioxide. It wants to make water. There must probably 1,000 elements it would easily form. But it's in the atmosphere as pure oxygen. Why? Because plants, photosynthesis plants and algae and cyanobacteria, those three, constantly pumping oxygen in the atmosphere. Nitrogen is nitrogen is inert. It's N2. It has its electron shells filled, so it doesn't want to react with anything, but it was put there by decomposing bacteria that broke down living things and pumped the nitrogen into the atmosphere. Living organisms have to have nitrogen to live, but that nitrogen is N2. It's inert. And so life has come up with nitrogen fixing bacteria that break that nitrogen apart and turn into something more usable to life. Make it available to life. So life is built from the bottom up. Life is built on the first organisms that appeared on the planet, and we do not know how life appeared. But if it weren't for nitrogen fixing bacteria, there would be no larger life forms, because nitrogen would not be available. I added in here this red line because we're so interested in carbon dioxide, which is up there on the top at 400 parts per million. So water vapor is more powerful than carbon dioxide as a greenhouse gas, and there's a lot more of it in the atmosphere, 2,500 parts per million. But people don't get worked up about it because you can't do anything about it. It's kind of an interesting point to me. And that's an average, of course. Water vapor varies. So here's the problem. On average, the sun heats the earth unevenly. The rays are, on average, direct at the equator or near the equator. Of course, it's tilting back and forth as the year goes by to 23 degrees. But the sunlight is, even though it's 93 million miles away, you wouldn't think a little tilt would make that much difference, but it does. So the sun's rays are concentrated at the equator and they're diffuse at the poles. And so the planet has to come up with some way to distribute that heat, or it would get too hot at the equator and too cold at the poles. Oh yeah. And the point, what that creates is wind. This unequal heating causes the air in the atmosphere to move The hot air wants to move to places where it's cooler, and the cool air wants to move to places where it's hotter, and we get wind. That's what creates wind. But it's so constant. I'm thinking of this. Gosh, I don't have it prepared because of my. There's this great webpage on the wind patterns on the planet, and they are in constant motion. I may try and pull it up at the end. I'd have to get rid of this slideshow to pull it up. It's just so beautiful and so dynamic. And one thing that struck me when I looked at that, it's just gorgeous, just gorgeous. These air currents moving both clockwise and counterclockwise, which is a curiosity. Why do they move in different directions? High pressure systems move clockwise and low pressure systems move counterclockwise. But what struck me when I was watching these air currents flowing around constantly in both directions on the Earth was at the same time, the Earth's crust is flowing under our feet into the mantle. And the ocean currents are flowing up from the Antarctic and up along the continents. It's all a flow. And that's how the heat gets redistributed. So like this, so the winds. So this is the pattern that the winds end up describing on the planet. I don't know quite why that's there, because seems like it skipped something. But it would be possible that the air is going to heat up on the equator. It's going to rise because it's warmer and active. It's going to cool and move to the north. And an idealized situation is it would just go to the poles and sink there and cool off and come back on the surface of the Earth. But, and even this is a slightly more advanced vision of air currents, but it's also idealized. It's not this clean. But partly due to the fact that the Earth is spinning. The Earth is spinning at 1,000 miles an hour at the equator. That's impressive to me. It bends the air currents to the right, and they end up broken up into these cells. They call them Hadley-Farrell and polar cells, so that air rises at the equator and sinks at that subtropical high, the Tropic of Cancer, and rises again and then sinks at the pole, like that. So this is that map of the world is global precipitation, and blue and purple are very high precipitation, like up to 2 inches a day, even huge amount. Well, that's on the equator. Look at how that's on the equator. And then at 30 degrees north, it's a desert, especially in the Sahara and into Saudi Arabia. And that's because the warm air is rising at the equator and cooling, and cool air cannot hold as much moisture. So it liquefies, it turns from vapor into water, and it falls as rain. And it falls as rain on the equator. And the equator gets far more rain than anywhere else. So we end up, I just pulled up the word wet, dry, wet, dry. This process of air heating and cooling, and as the air cools at the mid latitudes, well, when it's cool, it doesn't pick up moisture. Then there's another high pressure system to the north there, and there's more moisture there. So this is an interesting visual of actually the impact of the tilt of the Earth over the seasons. Up in the upper right are the months: December, January, February, March. And of course, as the solar radiation shifts on the planet, obviously the heat gain is going to shift on the planet. I think I pulled up here. So I pulled up an arrow in the upper left there to point out our area in Washington and Oregon and wherever else people are. But you can see that there's just no solar radiation to speak of in the winter. And then there's a lot of solar radiation in the summer, which is, a good start on explaining why we have the seasonal changes. Not that that's a big surprise, but it's interesting to see it illustrated like this. So there, I just stopped it. Sorry. Just stopped it. Stopped it. But we still have to get, to explain our weather, we have to get the moisture from the Pacific Ocean to move onto the continent. And as it turns out, the Earth is spinning to the right, and the air currents are pushed largely to the right, depending on their initial trajectory, which is to say they can go, when you see a map of air currents, they go in both directions. And we're going to try and talk about that. It's a tough subject, but so here's another global precipitation by month: July, August, September, October. So all of our precipitation is in the winter, the blue over there in Washington. And then by July, and I think I stopped it here in July, there's no precipitation. And it's in part because of the tilt of the Earth, which is completely due to that planetesimal that hit the Earth 4.5 billion years ago. So summer. This is a map of high pressure systems, low pressure systems in the summer. So a high pressure system in the summer, the continent is warmer than the ocean. So the land heats up, the air rises and creates a low pressure system. The oceans are cooler, so the air travels to the high pressure systems and sinks there. High pressure systems move clockwise. You can see these arrows. Where's here? These arrows are suggesting a clockwise rotation. Low pressure systems, here's a low pressure system. They actually move counterclockwise. Hurricanes are low pressure systems and they move counterclockwise. I'll give a shot at explaining why that is. It's a little hard to understand, but not at this moment. But so here we have a high pressure system that's picking up moisture, and low pressure system. This is a winter view. In winter, the land is warmer than the ocean, so the land becomes high pressure. The ocean becomes low pressure. It's picked up moisture. The air is rising, which means it's going to precipitate. And because the air flow is always to the right, this low pressure system is going to come over the continent and cause the precipitation that we've been getting for the last 2 months in the Met-How. So the Earth is spinning, and it affects the air patterns on the Earth, and it's called the Coriolis Effect. And it's illustrated in this little cartoon. If this guy was at the North Pole and he threw a ball to somebody at the equator, he threw it straight to him. Well, the Earth is moving 1,000 miles an hour to the right, and so this would be the actual pattern. And this is what happens with the air as well. It gets bent to the right. Sorry, this thing's got a mind of its own. You can't see this very well, but this is the same phenomenon. So low pressure systems are the ones that are going to rain because the air is cooling and it can't hold the moisture. So I think here I tried to explain why high pressure systems. So I brought up this little guy in the middle of this high pressure system. This is rotating clockwise. The air is always bent to the right, but it's bent to the right from an initial point of perspective. So the perspective for a high pressure system is the air is rising from the middle and bent to the right. You end up with a clockwise rotation. Low pressure system, the air is flowing into a low pressure system. So the perspective, here's this little guy, and that perspective, from his perspective, the air is still being bent to the right. This is the right, but it's now spinning counterclockwise. So we end up with these contrary air currents spinning to the north, spinning to the left and to the right, depending on whether high pressure systems or low pressure systems. Hurricanes are low pressure. They spin counterclockwise because air is rushing into these low pressure systems. So we talked about this last week, and I like it because it's chemistry, but it's very easy to understand. What's impossible to understand is where this arrangement came from. And we touched on that last week. I was struggling like, oh yeah, intelligent design. I couldn't remember the term intelligent design. You know, so intelligent design is used as a religious pseudo-Christian concept that all of this intense design of the planet was created by some sort of religious god. And that's not what we're talking about, but there is a patterning and design to the planet. And my favorite example is that you can fit 5 trillion hydrogen atoms on the head of a pin, and they all have 1 electron, but the shell holds 2. So is that design or is that not design? Not only does it hold 2, it wants to. It has an electromagnetic proclivity to join with other atoms. It'll join 2 hydrogens joined together and share their electrons, and they'll both have full shells. And you can have 5 trillion of them on the head of a pin, and I guess you'd end up with 2.5 trillion H2 atoms because they'd all join together on the head of a pin. So there's some pretty intense design going on. It doesn't mean that Christianity or Islam seems so ludicrous to me that we do that. So one of the themes, I mentioned this last week, one of the themes of big history is, the first theme is complexification, that the universe has grown more complex over time. Well, that's easy to substantiate. There were the only elements in the universe, it's thought, no one was there, but science thinks it's figured it out, was hydrogen, helium, and a little bit of lithium. That's all there was, 10 seconds after the Big Bang. So where did the other 89 naturally occurring elements come from? Well, they were forged in the cauldron, the cauldrons of stars, and in supernova explosions. Well, is that complexification or is it not? Yes, it is. And all of those elements have electron shells, and they all want their shells full, except for the ones that are full. And that's the noble gases, and their electron shells are full, and they're over there on the right of the periodic table, and they don't react with anything because they're happy with their electron shells full. It's, in my mind, it's just bizarre that the universe has this intricate, inexpressibly refined design aspect to it. It doesn't mean we can't draw any conclusions from that. It has other features like catastrophes, It's not, it's just phenomenal that this exists. Well, so this is water. There's a big story here, and some of it comes out right now. That upper picture is actually the way the hydrogen atoms align themselves in water. They're off to one side. They're not symmetrical. Water, as I have mentioned, is the second most electromagnetic of all the elements. And actually, I'm surprised that that's understandable why it's so electromagnetic. I shouldn't try to just explain it. But part of the reason is it has 8 electrons, 8 protons in the nucleus, and they're not very far from the electron shells. So they exert this positive pull out beyond the nucleus because it's a small but jam-packed nucleus. So oxygen will pull, because the protons are positively charged and they're packed in there in the nucleus, oxygen will pull electrons closer into its nucleus, which will leave the hydrogen positively charged. I don't know if you get that, but it sort of shows it here. There is a negative charge for the oxygen shown right here, positive charge shown here, because the electrons have been, they aren't pulled very far. It wouldn't be measurable, just a little ways, but it creates an electric charge on water molecules. That's why water molecules stick together. That's why water is water. They don't stick together very long. They shift. In a glass of water, they shift 1,000,000 times a second, but they do stick together. And that has ramifications for climate and weather. And this is, to me, this is chemistry, and it could seem boring, but it's easy to understand the facts that are coming forth here. And the reason are the hydrogen bonds that we just talked about. So it takes 1 calorie to raise 1 gram of water, 1 degree centigrade. Is that a coincidence of the universe? No, that is the definition of a calorie. So, to raise something else 1 gram of water, it would take a different number of calories. It's based on water. But look at this. So here we want to melt water from ice to liquid. It takes 80 calories to melt water from ice to liquid with no change in temperature. That is just shocking. Why is that? It's because of the hydrogen bonds. It's because the hydrogen bonds in ice become rigid, and it's hard to break them apart. It takes a lot of heat to get them to move, to get them to let go. Heat is all about movement of molecules. This is even more shocking. So now we're turning that liquid water into water vapor. It takes 533 calories to turn 1 gram of water from liquid to vapor with no change in temperature. So what? You could say, so what? This shows at the bottom the amount of heat being added to water with no change in the physical state of the water until after 740 calories have been added, it turns into liquid or whatever. It's really kind of a shocking fact. So this is my greenhouse. And humorously, to me, I took this picture last year, and this is exactly what it looks like right now. And by the way, I go out there with a push broom. I go inside and I hit it from underneath inside. You have to get the snow off of those greenhouses or they'll just be crushed. So it's off. That's what it looks like now, but that is from last year. When this snow melts, before it melts, it has to go through it has to absorb. This is the change from ice to water right here. It's going to absorb 80 calories of heat. It's not 1 calorie. It's not 1 calorie that's going to change it from snow to water. It's 80 calories. And to evaporate water, it's this large number here. So that has a huge effect on the climate because it moderates the heat gain in the spring. It doesn't matter how hot the day is. It's all going to be absorbed by the snow. And the air's not going to heat up because all the heat's being absorbed by the snow, which is slowly melting. We did this wet dry, but the southeast of the United States is not. It's at 30 degrees north, but it's not dry. It's wet. Well, there are other factors at play. That's certainly true over here in Southeast Asia at 30 degrees north. It's supposed to be in the dry zone. It's not. Why is that? And well, the reason is ocean currents. So this is a GIF. It's going to move here a little bit. So here's ocean currents. The blue is cold water. It heats up when it gets to the equator. It hits continent and turns out, and then it's going to, of course, cool off. There should be more yeah. So this is another factor in weather and climate, is this amazing circulation of the ocean currents. I saw the number and I do not remember what it was, but it's a huge number of gallons per second or per minute. They're flowing through the oceans. What are they doing? They're distributing the heat from the equator to the poles. And I think this is stop action here. You can see the heat moving south and north, and the cold moving towards the equator. So it evens out. So another Goldilocks effect. It says up top there, it says faint young sun paradox. So the early suns, I guess I'm trying to think of how we would characterize them. Certainly the astronomers. The astronomers understand that the sun was not as strong in the early days of the planet. So the sun and the planet are approximately the same age, 4.5 billion years ago. The sun would not have been as bright as it is now. So the Earth would have been cooler. So how was it possible for life to appear? And life appeared about 3.8 billion years ago, and the faint sun paradox lasted a long time. How is it possible for the sun not to be frozen, not to just be frozen? I mean, the Earth has frozen several times. Like at the end of the Permian, we had, they call it snowball Earth. The whole planet froze, almost the whole planet. Part of the answer to how the planet has managed to retain a livable habitat for life is that life has done that on its own. How has it done that? This is methane over time. These are billions of years, 1 billion, 2 billion, 3 billion, 4 billion. Life has pumped methane out of the atmosphere. Methane is a very powerful greenhouse gas. Life has pumped CO2. This is probably, I would guess this must be 1,000 parts per million, 5,000 parts per million. So, right now we're at 400 parts per million carbon dioxide. It was 5,000 parts per million. So what happened is that these greenhouse gases were much denser in the early planet and warmed the planet and made it possible for water to exist as liquid, which made life possible. And life started pumping oxygen in the atmosphere, and it's now 21% oxygen, whereas these greenhouse gases have been pumped out of the atmosphere by life. That is a Goldilocks effect. So these changes over time are interesting. So we sort of talked about the fact that there was really no oxygen. So this is 1 billion years ago. Well, the Earth, it's 4 billion years old. So life appeared 3.5 billion years ago. Photosynthesis, I actually forget when photosynthesis. It's photosynthesis that pumps oxygen into the atmosphere. It's a byproduct of photosynthesis. It is not a waste product of photosynthesis. It's always talked about as a waste product. It is definitely not a waste product. That oxygen then reacts with the other products of photosynthesis, the sugars, and releases the energy captured by photosynthesis in the sugars and makes life possible. It is not a waste product. But anyhow, there was none early on, very little or none. Okay, so an interesting aspect of this graph, which I think is accurate. I've read a few things. I mean, you never know if what people are feeding you is accurate, but I've seen several references to this in the last week, where in fact oxygen now is 21%. This red line, it spiked to 31%, 35%, 300 million years ago. I don't think it's understood why. This is when those gigantic insects existed. There were dragonflies that were a foot in diameter, because dragonflies don't have lungs. The oxygen necessary has to diffuse in through holes, spiracles in their bodies. That's the only way they can get the oxygen they need. Well, if there's 35% oxygen in the atmosphere, there's no problem. You can get a lot bigger. And so there were millipedes a foot long, and there were dragonflies a foot in diameter, a foot long, and things like that. But I don't know exactly what happened in here. There are stories in the scientific books about it. But for one thing, you're going to have incredible fires. It's going to be impossible to put fires out at 35% oxygen content. It's like my little stove over here. When I want it to burn, I blow on it, increase the oxygen supply. So it has leveled out at 21%, which seems to be a happy medium. It's enough for life, but the fires don't rage totally out of control. Yeah, these get a little complex. They're not too hard to get onto. So the black line is carbon dioxide through time. So here it is at 7,000 parts per million, 500 million years ago. Drops way down, goes back up, and goes down to our current 420 parts per million that it is today. The point really to me is only that these things change over time. There's a lot of shifting over time. The blue line, what is the blue line? Temperature. This is temperature over time. Well, I mentioned there have been two snowball Earths. This is a snowball Earth right here. And this is a snowball Earth. I can never remember which period this is. And at the moment, I can't remember. It's over there. But an interesting thing here is that I know this is heretical, but look, the temperature is not only is it not very closely associated with the carbon dioxide quantity in the atmosphere, it's not associated at all. It's not associated at all. There's just more to the stories. If I could make a point, and I haven't lost people because of my heresy, I would say the system is more complex than we understand, and we should not pretend that we understand everything about how our Earth system functions. We should try to understand it, but not get, totally bent out of shape. And to make that point, how much do we actually know? How much do we know about the way the Earth functions? Well, so this is an interesting film. It's on YouTube. If you Google photosynthesis at MIT, you can watch it. It'll come up. And it's 20 years old, but I think they still wouldn't know the answer to this question. So graduating MIT students were given a seed. So they have a seed in their hand. And then they were handed a piece of wood. And they said, where did the wood come from? These guys are graduating from MIT, the most celebrated engineering school in the country. Where did the wood come from? And they say, dirt. They think that plants are sucking up dirt. And, there's no hole. Well, the actual fact of the matter is plants are making their organic matter out of 90% carbon dioxide. The biosphere, these trees, 600 billion tons of biosphere on the planet. It's appearing out of a gas that exists in the atmosphere at 400 parts per million. It's mind-blowing. It's totally mind-blowing that this could be the case. This is the truth. So this is what they tell them. They said, well, what would you say? She says to this guy, what would you say if I told you this was made out of carbon dioxide in the atmosphere? And he says, I would say that would be a very strange idea. It is a strange idea. Watch it. It's quite good. It's a strange planet. So this is a fun graphic, really, of the life on the planet by weight or mass. So most of the life on the planet, this is the 1, 2, 3, 4, yeah, 6 kingdoms of life. 1, 2, 3, 4, 5, 6. 6 kingdoms of life. Viruses don't rate as life, they're so interesting, but they don't rate as life. So most of the life on the planet is plants. This is billion tons, 450 billion tons. And they say carbon, as if plants are all carbon. They're not all carbon. I don't know why they do that, but maybe they do mean carbon and they're not counting the other stuff. But in any case, this all is appearing from carbon dioxide in the atmosphere. And it's totally mind-blowing to me. And the animals are just a hangnail on the biosphere because they're totally dependent on the plants capturing the energy of the sun and the algae, which are protists, capturing the energy of the sun. And then the fungi appeared because other living organisms couldn't figure out how to break down lignin. The plants had figured out how to create this wood, which is such a tough structure. And one of the only things that can break it down is fungi. And so it took them a while to appear. Sorry about all these graphs. Earth temperature through history. This is hotter down here. It's upside down from the last time. Earth temperature through history. Hot, cold, hot, cold, hot, cold. Hot, hotter, very hot. And now some sort of midline. And this is the Pleistocene. So this is colder. Up here is colder. Well, there have been 20 glacial advances in the last 2 million years. That's also shocking. And we don't really know why. People talk about something called the Milankovitch cycle, Milankovitch cycles, but I don't actually think that's the answer because there were 10 glacial advances, big ones, but then there were 10 smaller ones before that. And it just doesn't I don't think Milankovitch really fully explains. We don't know why. And we're in an interglacial right now. I don't know, let's see if there's anything else on there. These graphs are fun to pick apart, but nothing's particularly striking me right here. This is the Met-How. This is precipitation in the Met-How. If I had to go back and get this offline, I don't think I could find it, but I remember I poked around and was able to find this. This is precipitation in the Met-How from 1910 here to 2020 here. So this is annual precipitation. This is 20 inches, 25 inches. So can't quite read this. 10, is that 20, 30, 40? Look at how much rain there was. Oh, 1948. That's when the flood was. That's when the flood took out the bridges and they had to get that water out of here. So the interesting thing to me is in 1918, there was 5 inches of 5 inches of precipitation. And in 1920, there was 4 inches of precipitation. And that's what drove the upland homesteaders off of their farms. When I came here in the 1970s, there were falling down houses everywhere in the uplands in the Met-How because they had been driven out of there 20 years before because all of their wells went dry. Because the climate changes, it changes all the time. It usually stays within the parameters necessary for life, so you can only hope that it stays in there. And this is similar down here. This is a graph of drought in New Mexico over the last 2,000 years. And these are wet periods. And these are dry periods down here, the brown. So it's just another illustration of what we're faced with, that the climate changes, whether we like it or not, and whether we understand it or not, it changes. So times the river of passing events, I just love this quote. He just poetically addresses the fact that everything changes over time. And all we can do is enjoy the flow. And that might, yeah. I think that's the last slide. So I survived. I wish